Hey there, guys. So in this lesson, we are going to learn how to solve systems of inequalities where you have more than one inequality. The variables mean the same thing. You can graph them on the same set of axes. And what makes solving systems of inequalities so devilish is that there's a set of solutions. And sometimes that set of solutions is a little bit hard to describe algebraically. So sometimes you just have to show it graphically. And so that's the technique we're going to look at for solving systems of inequalities, how to graph it and how to find a region that it meets the constraints of both inequalities at the same time. You see, in a system of equations, you often have just one place where the lines cross, and that one place is the solution to both equations simultaneously. However, with the system of inequalities, each inequality has a region that represents the solutions, and it's the place where those regions overlap that is the solution to that system of inequalities. So let's take a look at how to graph them. So a couple of tips when it comes to graphing a system of inequalities. If the inequality has a greater than or a less than like plane, you're going to use a dotted or dashed line because that line isn't in the solution set. If it has a greater than or equal to or a less than or equal to, you use a solid line, and that shows that the line is in the solution set. So you can be right on the line and you're in the solution set. You shade in the area that makes each inequality true, and the solution set for the system is where both of those areas overlap, and that's your solution set. Systems of inequalities, I don't tend to solve them like this in real life situations, but I do tend to solve them like this in computer programming situations, computer graphics, games, things like that. It's really common to use systems of inequalities to map out regions on your screen. So this little contrived situation maps out regions in a park. In this situation, members of a high school math club are doing a scavenger hunt. 3 items are hidden in the park, and the park is a rectangle that measures 50 meters by 20 meters. So since it's a perfect rectangle, you can make it into an XY coordinate plane and use these systems of inequalities to give you clues where the treasures are. So in the first system, we have this situation. Our first inequality is y is greater than 14. So we're going to find the line that represents y equals 14, and so that'll be somewhere around here, and we'll plot it using a dotted line because the line isn't in the solution set. The line is, since it has to be greater than, y can't be exactly equal to 14. Since the inequality is y is greater than 14, we shade in the region above that line, where the y coordinates are bigger than 14. Next, we're going to graph the inequality x is less than 10, and I'm going to use a different color here. So for x is less than 10, we'll draw a line at x equals 10, and it's going to be dotted because x equals 10 is not in the solution set, okay? And then the inequality x is less than 10 is everything that's on this side of the line. So the solution to this system of inequalities is the place where those 2 shaded regions overlaps. And that's this little rectangular area right there. And I'll even shade that in with a different color so we can demonstrate it right in this area. So that area right there is the solution set to the system of inequalities, and that's where that scavenger hunt clue is. Okay? Next situation. The first inequality is x plus y is greater than 20. Well, just like we did before, we're going to graph the line x plus y equals 20, and then we'll figure out what regions shade in. When it's written in standard form like this, it's really easy to graph using x and y intercepts. So first plug in 0 for the x, and if x is 0, 0 plus y equals 20, so y must be 20. And then plug in 0 for the y. If y is 20, if y is 0, x must be 20, so 20 comma 0 is also on the graph, and then we can draw a straight dotted line in between them. So 0, 20, and 20, 0, and we'll draw a dotted line going between those points. That's the graph of the line x plus y equals 20, but we can't be right on that line, and now we've got to figure out what side of the line to shade in. So let's pick a point that is in one of those regions, like here, this is 5, comma 5. If x is 5 and y is 5, 5 plus 5 is 10, 10 is less than 20, so this region is the one that you shade in. Okay, the next equation I'm having trouble seeing is y is greater than 6. So I'll use a different color for that one. Sorry, that's x is greater than 6. So I'm going to find the line x equals 6, and I'll draw a dotted line there because it's not equal to 6, it's greater than 6. And then I shade in all the region that represents x greater than 6. So that's this whole area over here. And then the solution to our system of inequalities is where those two shaded regions overlaps. So that is this little triangle-y area here. That is the solution to the system of inequalities. That's where both inequalities are true at the same time. Okay, and so 5, 5 is in there. 10, 10 is not in there. That's like on the line, and we need to be on the side of the line. But like 9.5, 9.5 would be in that region more than likely. So next we've got this system of inequalities, and you're going to see clue number 3 is kind of special. So since these are in slope-intercept form, the first equation has the y-intercept at plus 20, so we'll put a dot right there, and the slope is negative 2, so you go down 2 over 1, down 2 over 1, and there's our first line, and that's a less than, so it's dotted. And since y has to be less than negative 2x plus 20, plug in 0, 0. Negative 2 times 0 is 0. Y is 0. So 0 is less than 0 plus 20. Yes, that's true. So this region is the one that's shaded in. Okay, the next line, I'm going to pick a different color, is y equals negative 2x plus 10. So I'll put a dot at 10 because that's the y-intercept, and then down 2 over 1. This dotted line represents that equation, and I'll kind of shortcut this process. This region is the one that's shaded in. So what makes this system of inequalities kind of weird is that the solution for this one is really the only one that matters. They're two parallel lines. The solution sets are on the same side of it, but this region down here is the only place that's in both of those systems of inequalities at the same time. So that region is the solution set for that inequality system. This next one is really special, and you'll see why. So clue number 4, we've got one equation, which is y is greater than or equal to x plus 10. Again, this is in slope-intercept form, so the y-intercept is right there. And since the slope is 1, we go up 1 over 1, up 1 over 1, up 1 over 1, all the way up here, and this is a solid line. I'm going to pick a point here, like let's say 5, 25. So if 25 is y, is that greater than or equal to 5 plus 10? Yes, it is. So this region is the one that's shaded in. Okay, then we've got the inequality x is greater than y. So for that inequality, we graph the line x equals y, and it's a dotted line because there's no greater than or equal to in there. Okay, and that, again, it has a slope of 1. It's all of the points where the x-coordinate is equal to the y-coordinate, but we're looking for the places where x is greater than y. So like let's look at here, which is 10, 0. If x is 10 and y is 0, 10 is greater than y, so this is the solution set for that inequality. This is a unique situation because in this one situation, there's no overlapping region for these two inequalities. They're parallel lines, and their solution sets are on opposite sides of those parallel lines. So this is one situation where you can say no solution. There's no place where both of those situations are true at the same time, so you can't find any graphical solutions to that inequality. So that's how you find solution sets to systems of inequalities. And when you describe those solution sets, you really just describe them as the system of inequalities. So the biggest clue is understanding how to go from that system to a graph, and then being able to interpret a graph and go back to the system. I want to do one word problem with you to show how systems of inequalities can show up in real life. So let's get rid of my notes here and go on to the next page. Down here, we've got a situation that you may run into in real life where you're a business owner, and this is a hairstyling business. So the stylist charges $15 for a haircut and charges $30 for a hair coloring. I'm going to skip around in the word problem a little. The hairstylist has to make a minimum of $150 a day. The haircut takes on average 30 minutes, a coloring takes 2 hours, and the stylist can work up to 8 hours a day. So there's two different inequalities implied in this situation. One is that you have to make a minimum amount of money, and the other is that you have to work a maximum amount of hours. And we can represent those two situations with inequalities. So the first one for the money would be 15x plus 30y. It must be greater than or equal to 150 because the word problem says a minimum of $150 a day. She can make 150 and she can make more than 150, and that's okay. Next is the time constraint. So it takes a half hour to do a haircut, so I'll write that as 0.5x plus it takes 2 hours to do a coloring, so 2y, and then she can work up to 8 hours a day. So 8 hours is okay, and anything less than 8 hours is okay. So this is less than or equal to 8. Okay, now for this one, I'm going to cheat just a little bit, and I'm going to plug these equations into Desmos, and then we'll color in the solution set once we've graphed the lines there. Ordinarily, we'd graph the lines manually. We're just taking a little shortcut here. So let me go to Desmos, and I need to turn off the drawing tools, so hopefully I can remember what those equations were. So the first equation was 15x plus 30y is equal to 150. So I'm ignoring the inequality for right now. The next equation was 0.5x plus 2y equals 8. So just looking at these as lines. Now this blue line represents all of the possible numbers of haircuts and hair colorings that she can do to work exactly 8 hours. And then the red line represents the number of haircuts and hair colorings she can do to make exactly $150. But what we want to figure out is which region here is the one where she can make 150 or more and work 8 hours or less. So the key is, I'm going to grab a pen so we can start shading some things in. I'll grab a blue pen for the blue line. So for the blue line, let's pick a number of haircuts and hair colorings. Let's say here at 6, 1. So 6 haircuts, 1 hair coloring. 0.5 times 6 is 3, and 2 times 1 is 2. 3 plus 2 is 5. That is less than or equal to 8. So as far as like working for a certain number of hours, the region that is valid is the region that's below this blue line. So we'd shade all that in. This is the valid number of hours that she can work. Okay, all that region there. And then we'll take a look at the red equation, and I'll use a red pen. So again, let's pick a number. We'll pick again 6, 1. So if she does 15 times 6, that's, oh gosh, 90. And then 30 times 1, add that on to 90, that's 120. And that is not greater than or equal to 150. So this is not the side of the red line that's shaded in. The side of the red line that's shaded in is this side. Okay, and you can start to see there's a region where the red and the blue overlap. And that region is that kind of triangle-y shaped region that's below the blue line and above the red line. So this green area is the sweet spot. That's where she can work a maximum of 8 hours and earn a minimum of $150. So it will help her budget her time if she knows she can do, for example, 12 haircuts and 1 hair coloring, or 10 haircuts and 1 hair coloring, or 8 haircuts and 2 hair colorings. All of those values are valid, but she can't do, say, 6 and 1, and she can't do like 12 and 2. Those would be out of that sweet spot region. I'm going to show you one more tip with Desmos just because it's a cool feature. I went through all that, and it turns out Desmos is actually capable of doing inequalities. So now you know. The way that you do it is if you're going to do a greater than or equal to, you type in the greater than and then you type the equals right after, and then it even makes the line solid and it shades in the region above it. So that's the inequality 15x plus 30y is greater than or equal to 150. And if I get rid of the equal sign, you can see it even makes the line dotted. So it's kind of a cool feature. And then this has to be less than or equal to 8. So now you can very clearly see that region where the red and the blue lines overlap. And this area right here is where she can earn her correct amount of money and work her correct amount of hours. So the problem set that goes with this is a set of Khan Academy problems. It has you look at systems of inequalities and then create graphs of them and match the graphs with the system. So I think it was a pretty good problem set, and I hope you enjoy it. And we'll do a project on inequalities toward the end of the week. Thank you for listening.